Hi everyone. Today we will learn about the learning curve theory. So before start, let me briefly recall that what we discussed in our last lecture. So in our last lecture, we have learned about how to manage the capacity, right, by using the product mix, the linear programming formulation. And we need to define the objective function in this way. And we have different source of constraints. One is the capacity constraints and one is the demand constraint. Okay. And then at the end of the last lecture, we discussed several examples about why the efficiency, utilization, or other derating factors are critical and how they will affect the real cases when we do the capacity planning. And in addition to that, one thing we also need to consider is the learning rate change if we repeated to produce some units, some products, some production. So like the slide explains here, the learning curve theory, it is a concept used in production and operations management to model how labor efficiency improves as workers gain experience producing more units. So the theory is based on the idea that as the cumulative quantity of units produced doubles, the time required to produce each unit decreases at a constant rate, as shown here. If we assume that for the first unit produced, then the average time needed is 100 units. And then for the second unit of to produce for the same production, then on average the time needed is decreased to 90%, 90 unit. 90 time units if the learning rate is set as 0.9. The theory is based on the idea that the cumulative quantity doubles. And the learning rate here, I equal to 0.9, we call this number as the learning rate. The practical implementations for the learning curve is that we can reduce the cost, right? As workers or machines gain experience, production becomes faster and cheaper. So in this way, the cost will be reduced. From another perspective, for learning and forecasting, companies can use the learning curves to forecast the labor cost and set realistic production schedules. And for learning rate, if we consider learning rate, we can also benefit for process improvement. In identifying a learning rate can help in optimizing the processes and improving productivity over time. So it's meaningful for us to consider the learning curve when manage the capacity, when do the capacity planning. Here is an example that with different learning rate, how the time unit required for each for producing each unit is required. So it is a decreasing curve with different rate. And here is the derivation of alpha, where alpha is needed in the formula to calculate the average time to produce one unit at the unit n, at the nth unit. So by definition, we can know that the learning rate L is defined as the time to produce unit 2n divided by time to produce unit n. So this is a number defined as learning rate. Okay, then by using the formula, we can get that k times 2n to power of minus a over k times n to power of minus a equal to the learning rate. Then take 2 to power of minus a equals to the learning rate. Then take the logs for both sides of the equation and solve for alpha. We can know that alpha can be described in this formula. Okay. Then we move to the average time per unit up to unit n. So this is the formula that can be used to approximate the average time per unit over the cumulative production up to the nth unit, capturing the effects of the learning curve across multiple units. And maybe you will ask that why we need to use approximation instead of directly use the formula, right? Actually, calculating the average time per unit exactly can be quite complicated because each unit's time decreases nonlinearly as production continues. Then in this formula can provide a simplified, approximated solution that is computationally efficient and sufficiently accurate for the practical purpose. Here are some detailed explanation for different terms. Firstly, for the adjustment for learning, we use this term to reflect the cumulative learning effect over the production of multiple units. And we also divided the whole formula by n, which means dividing by n gives the average per unit. And the factor here we'll use another factor, which is 1 minus alpha. So this factor adjusts the rate of decline in time based on the learning curve, ensuring that the average time reflects the learning rate. So in this approximation formula, we also consider the learning rate in it. And here are several typical learning rates that we will use in different scenarios. If for large or fine assembly work, we set learning rate quite low, which means as the number of units increased, the efficiency of workers or machines will be relatively largely improved. And for some welding work, learning rate will be set between 0.8 to 0.9. And for some machining work, learning rate is relatively high because even though the total number of units is quite large, the potential to improve the working efficiency is not very high. Okay, here is an exercise to detailedly learn about how to use the learning rate. So what cost and unit of direct labor would you recommend charging on a new assembly if you know that the first unit assembled took 6 hours to complete? And the cost of the direct labor is estimated at $8 per hour, and you will only need to build 15 units. Then this is we assume that it is a complex assembly work, and you would expect a relatively slow learning rate. And here is an example. So for the assembly operations, we just like we mentioned, we will set the learning rate to 0.7 to 0.9. To 0.8. So here we will assume the learning rate equal to 0.8 because it is a quite complicated assembly operation. Then here's the curve, and then the red line is the average the working rate. So the average time required for each unit. Then using the approximation, we know that we can calculate the approximation by this formula, right? And we also know that the learning rate equals to 0.8. So according to the learning rate, we can calculate it alpha by using learning rate. So alpha is equal to 0.32. Substituting data in the above equation, we can get the following solutions. Therefore, we can know that the average time per unit is 3.42 hours per unit. And I also want to mention that it is very close to the true value we calculated before. Let us revisit the previous slide. So just like the slide shown here, the true average time required for each unit equals to 3.4, which is very similar to the results that we calculated by using the approximation formula, right? So we can now estimate the total direct labor content per unit by using this formula. We use the average time per unit, which is calculated in the previous slide, times the cost per hour. Then we can get the average, the cost of direct labor equals to 27.2 per unit. Okay. So far, we have learned how to use the learning rate and how to calculate the approximated average time units required for each unit by using the approximation formula, right? And here are several questions. The first one is, how would the cost estimate differ if we ignore the learning effect and assume all units will take as long to produce as the first unit? Then the first question asks us, what will happen if we just ignore the learning effect? So actually, by calculation, we can know that the estimated cost per unit equals to 48 if we ignore the learning effect results. So we can see that the estimated cost per unit compared to 27, which is a much higher cost estimate because it does not account for the expected reduction in time per unit as production experience increases. Okay, and for the second question, how long will it take to complete all the units, with and without consideration to learning? So the total time to complete all 15 units would be approximately, if with learning effect, which equals to 22 hours. And if we do not consider the learning effect, then which equals to 90 hours. Okay. You may wonder that how these are calculated. So if we do not consider learning rate, which means we assume the average time required for each unit will not change as the number of production increases, then which means we assume we need 6 time unit for each unit when we try to produce 15 units. Right, then the total time required equals to 6 times 15, which equals to 90. And for our cases, if we consider the learning effect, which means we can use the average time per unit, which equals to 3.42. And then if we consider the learning rate, the total time required to produce 15 units equals to this number 3.42 times 15, right? Which equals to 51.22 hours. And the last question is that what repercussions could it have on your business? So the question led us to consider if we consider the learning rate or consider learning effect or do not consider learning effect, what is the difference? So overpricing or lost the competitive edge or the efficient resource allocation or inaccurate financial forecasting and budgeting. So these kind of things will happen if we do not if we do not consider the learning effect. Okay, so for this question, we also know how the learning effect will impact the real applications and how important that we need to consider the learning effect. Okay, then that's all for this chapter for the capacity planning.